Okay, so I think it's good time to start our colloquium today. So, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests, participants, ladies and gentlemen, good afternoon, and welcome to the Department of Mathematics, Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, Yogyakarta. Before we explain what event today is, let me welcome our special invited guests who spared their valuable time to make this event so meaningful for us. Her Excellency Dr. Norma Yulia Megawati, the Secretary of the Department of Mathematics, Universitas Gadjah Mada. The speaker of our colloquium today, Mr. Nankun, PhD, and all participants of the colloquium. First, I would like to introduce our speaker for today. So, yeah, Nankun is I can say that in terms of partition theory, he is my best friend because, yeah, we started our PhD together and then we finished almost at the same time because he finished earlier, maybe around 2 months earlier. And he graduated his undergraduate and also a master from Suzhou University, and he get his PhD from Nanyang Technological University. And for today, he want to share with us about partition theory. But before we listen together about the presentation, we would like to invite the Secretary of the Department of Mathematics to give an opening remarks and also to open the program officially. So to Dr. Norma Yulia Megawati, please.
Thank you, Mas Tuha. Assalamualaikum warahmatullahi wabarakatuh. May peace and God blessing be upon you all. On behalf of the committee, first of all, allow me to extend my warmest greeting and welcome to the Algebra Colloquium organized by Algebra Laboratory, Department of Mathematics, Universitas Gadjah Mada. One of the goals of this event is to improve the academic atmosphere in the university. With the theme of construct new identities from Ramanujan tree identities, this colloquium is aimed to pull together researcher, lecturer, and student to share their critical thinking and research outcomes. Distinguished guests, ladies and gentlemen, this colloquium will be far from success and we could not accomplish what we do without the support from various parties. So let me extend my deepest gratitude and highest appreciation to our speaker, Dr. Hong Nankun. I would like also to thank each of the participants for attending. And should you find any inconvenience and shortcoming, please accept my sincere apologies. To conclude, let me wish you fruitful discussion. And with that, I declare the algebraic colloquium open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Wassalamualaikum warahmatullahi wabarakatuh. So thank you for Dr. Norma to open this colloquium officially. And I'm sorry. Okay, so sorry. Because now I'm online near my garage. So when my wife tried to start the car, then the sound will be coming. So sorry for the interruption. And yeah, I think let's start the presentation right now. So yeah, Nankun will present about this result. I think this one should be some of your result in your PhD, right?
Yeah, some from my PhD thesis and one from the latest paper.
Okay.
Published.
And you just published it last year. In Ramanujan Journal.
Yeah.
Okay. So please.
Yeah. Okay. So let's begin the talk. So first, I want to thank the university. Sorry, I don't know how to read the name of this because it's not. I think it's not English, right?
Yeah, Gadjah Mada. Gadjah Mada is the name of general in the past.
Okay.
So there was a kingdom in Indonesia. Yeah. Okay.
And thank Wuha for inviting me to give this talk. So I have a chance to share some some things from my research. So firstly, I want to introduce some very fundamental things. If you doing the partition theory, so you will be very familiar with these kind of things. The first thing is the partition function. A partition of a positive integer n is a sequence of non-increased positive integers which add up to n. And here we use this notation Pn to count the partitions of n, and we agree that P0 is 1. So here we give an example that for the partition of 4, we have totally 5 different partitions. The first one is 4 itself, then we can write it as 3 plus 1, and 2 plus 2, and 2 plus 1 plus 1, and the last one is 1 plus 1 plus 1 plus 1. So we know that P4 equals to 5 here. And then we got a generating function for Pn. This is known by, is proved first by Euler. And we introduced the new notation, QQ infinity. So if you are not doing this kind of things, I think you can just remember, if we meet this kind of thing, it represents an infinity product. Okay, so it represents some production. So for the generating function here, you can write this as this kind of thing, some infinity production. And using this kind of thing, we can see how to get the generating function. For example, we still use this P4 as an example here. So first, the 4 itself, we can see there, we can use this Q to the power of 4 to represent this 4. So we get one possible thing, one Q4, Q to the power of 4 from here. And then we can write 4 as 3 plus 1 here. So how to read this kind of thing in this production? We can see here the 3 here, so we can find the Q to the power of 3, Q cubic here. And then for the 4, we find a Q here. So if we times these two things, Q cubic times the Q, we got another Q to the power of 4, right? So we got 2 of Q to the power of 4 now. And for this, for 2 plus 2, here we have 2 same things. So we can read the thing here. Start from the Q square, and Q square times Q square, we got Q times Q to the power of 4 here. And again, we got another Q to the power of 4. So we already get 3 things here. And then we just read the residual 2 cases. The first one is 2 plus 1 plus 1. So we find the 2 here in this bracket, start from the Q square. And then 1 plus 1, we can get the Q cubic from Q times Q itself here. So we times this from this. We use Q square times Q square. We can get a Q to the power Q to the power of 4. And the last one is 1 plus 1 plus 1 plus 1. Then we get a Q cubic or Q to the power 4 straightly here. So this is the idea how to get the generating function of Pn. And using the circle method, Hardy and Ramanujan obtained a asymptotic formula for the Pn here in 1918. And then later, the Rademacher, when he prepared the lectures, he improved the circle method and get a very explicit formula for the Pn. Involve some sin edge function here. And Ramanujan has 3 very famous congruences for the Pn. The first one is this: the P of 5n plus 4 can be divided by 5. And another one is this, and the last one is this. So Ramanujan himself have already proved this kind of things, and Freeman Dyson want to provide some combinatorial interpretations for Ramanujan's congruences. So he defined the ranks, and the ranks or the rank of a partition is defined as the largest part to minus the number of parts. So here is an example. For example, let's see this first. For example, we have a partition of 14. The partition is 6 plus 4 plus 3 plus 1. So we have four parts here, right? And the largest part is 6 here. So the rank of this partition is the largest part here, 6, minus the number of parts here is 4. So it should be 6 minus 4 equals to 2. And to explain it geometrically, we can say if we represent the partition like this, this is the first part, and this is the second part. And so we can see the largest part is the number of square here in the first line. And the part here is how many lines here we have. So it should be this one minus this one. So we can say in fact equals to this. If we write a line with slope 1, we can get the rank should be the number of square here. Okay, so Dyson's rank can explain the congruence for the Pn modular 5 and 7. And the rank cannot explain the last one, the Pn modular, the last congruence, the Pn modular 11. And we use this notation n of m and n to count the partitions of n with rank m. And here we use this kind of notation n of m, s, and n to denote the number of partitions of n whose rank is congruent to m modular s. Okay, so as we mentioned before, the partition of 4, the Pn of the P4 is 5, so we have five different partitions here, and we just calculate all the ranks here. The first one is 4 minus 1, because the largest part here is 4, and it only has one part, so the rank here should be 4 minus 1 equals to 3. And for this one should be 3 minus 2, and same thing for the residual, the last 3 kind of thing. We can calculate the ranks here, 0, minus 1, and minus 3. So we can get this kind of things. So if we try to calculate the n of minus 3, 4, the n here should be 4. And m, the rank of m, if we try to calculate how many partitions of 4 with rank minus 3, we can see here, from here, it should be 1. Okay, and here we give the generating function for the rank, the n of m and n. It should be, looks like this. And we will try to deal with this kind of thing to study on the rank. So using the generating function is one useful way to research the rank, to study the properties of ranks. Okay. And I'll give some idea of how to get this kind of thing. So we can see from the generating function of partitions is q infinity here without any other parts. So the q of n square here represents the biggest square in this symbol, in this graph. For example, for this partition, the largest square here should be this one, right? Because if we want to find 3 times 3 square, we cannot find it, and the 1 times 1 is not the largest. So this 2 times 2 square is the largest square in the graph. So this q to n of n square comes from here in the generating function. Then we can just try to write the generating function for all the square, I'll use another word, use grids, the tiniest grid, the number of grids here on the right of the square. We can just write the generating function for this. It should be here. And then we just write in another direction. We write all the possible grids below this square. Then we write this part. So we get the generating function for the ranks. Okay. And Dyson gave the definition of ranks, but he did not prove that the ranks can interpret the congruence from Ramanujan. So he just conjectured that these two kind of relations hold. And later, Elkin and Swinton-Dyer proved that these two, these two identities are correct. Okay, then many researchers began to study on the ranks, but as I mentioned that the ranks of partition cannot explain this congruence. So Dyson conjectures that there is another partition statics congruence, which would explain all the 3 congruences at the same time. And finally, the Andrews and Frank Gavin found the cranks. And the cranks can explain the 3 congruences together. This is another story, okay? So here, we will use this notation, G of ZQ, to denote the generating function of ranks. And here we define a very special case for this. F sub A of Q is to represent this. And in fact, this is just some roots at the unit circle. So we can just ignore the explicitity, just ignore this, how to say? We just remember that the G of ZQ and F sub A of Q is the generating function of ranks. Then we can try to get an idea of the theory we will see later, okay? And the last thing I want to introduce is the definition of the dissection. Dissection is a very useful method to study the rank, because using the dissection we can get some relations of ranks and get some identities from ranks. So let's Pn denote any power series in Q. Then the T dissection of this power series is given by this kind of things. We just pick up the power of Q according to the congruent modular the T. Okay, so here is a very trivial example. If PQ is this Q plus Q square until the Q to the power infinity. Very trivial example here, the 3 dissection of P can be this. The first part is Q to the power of 3k, and then we times a Q here, and then we times another Q square here. So we get whole PQ here, and with 3 parts. Every part has all the Q with power congruent to the different integer according modular T. Okay, so all the Q here, we know that all the Q have a power congruent to 1 modular T, and here is modular congruent to 2 modular 3. Okay, the T here is 3. And all the power of Q here can be divided by 3. Okay, so let's say the motivation of our research is inspired by a paper given by Andrews and my supervisor and others. They gave new proofs of 4 identities of Ramanujan, and the most difficult identity proof among the 4 is this. And here, the phi, theta, and the per se is one is the generating function of Q, and another one is infinity production. So in fact, it relates the generating function of ranks modular 4 and the generating function of ranks modular 8 here. So we want to get some similar things. I mean, we want to get some identity relate the generating function of ranks modular 3 and modular 9. And this proof relies on the 2 dissections of rank modular 4 and 8. And the 2 dissections of them have given for the first time in their paper. And as a corollary, they got some relations of ranks here. It looks very simple, and I can see some beautiful. I can describe it as beautiful here, right? So we want to try to get some similar relations also. This is Dyson's result is a little bit similar here, right? And we already know there are some results about 3 dissections of ranks modular 3. So our aim is to get the 3 dissections of ranks modular 9, and then try to compare them to get some new identities. And the new relations looks like this, okay? So this is our result. The zeta is a primitive nice root of unity. So it means the rank of the generating function of ranks modular 9 here. And we already, the theorem here is a 3 dissection of the ranks modular 9 here. The first line is we can see all the power of Q here can be divided by 3. And for the second line, all the power of Q here has a power congruent to 1 modular 3. And for the last one, the power of Q here is modular 2 congruent to 2 modular 3. And for the J symbol here, it's just some infinity production. Okay. So let's see a sketch of proof how to get this kind of thing. We have a corollary here. We represent the generating function here as 3 parts. The first 2 parts involve a function named M. M here is a Lambert series, and the last part is an infinity product. So if we want to get the 3 dissections of the generating function here, we have to get the 3 dissections of the M here, the M here, and the J1 here. For this part, the J sub 3 and J sub 9 has been written in the form of power of with a Q of power of with power can be divided by 3 here. So our first aims are to get the 3 dissection of this M. So if we use this M as an example, we just take this definition into it and try to write this Q in the form of this. Then we try to get the three dissection of them. We have a useful tool here. It comes from my supervisor's paper. You can write the infinity product into the summation of some Lambert series. And the IDEM symbol here means if we write a F and this symbol, it means we got a cyclic summation of them. We just write the B1, B2 to BM first, and then swap B1 and B2, then swap B1 and B3 and until the BM and B1. And use this, we can get some, we can take some R and S in this formula, and we will get something like this. Then we can try to take different B and C into the identity here we get. Then we can deal with all the Lambert series in the previous page we see of the M function. Then we can try to cancel some of them and to get some useful thing. Then after getting the three dissection of this M and this M, we will see we can cancel, we can eliminate a lot of parts. And the last thing is to get the three dissection of this thing. And in fact, we use the maple to get the three dissection of this firstly, then we try to prove it. And when we just take all the three dissection here and we complete the proof, that's we can get this kind of things. Okay, and why we keep this kind of Lambert series here? Because if we see the three dissections of the ranks modulo 3, we can see they also there are some also we can also see this Lambert series in the previous result. So we can compare the coefficients, and then we get this kind of identity. And here, the C function here is infinity function. In fact, it's a generating function of cranks. And the F, all the F here are generating function of ranks modulo different integers. For example, F1 here is a generating function of ranks modulo 3. And here is a generating function of ranks modulo 9. So we got an identity related the generating function of ranks modulo 9 and the modulo 3 and 9. So as we wished, we found something here. And from three dissections of ranks modulo 9 and 3, we got some relations here. So this is something about the paper my supervisor and I published. And then later, I found another interesting. So first I want to write down to list the 4 identities of Ramanujan here. And in fact, it's the same 4 identities in the paper I just mentioned, which inspired us to get a 3 dissection of ranks modulo 9. And here are 4 identities here. I found a lemma. If we use lemma, apply the lemma into these 4 identities, we can get some new identities. So that's how to construct the new identities from Ramanujan's identities. But here are 4 identities here. We will see later how to get the new thing from them. Okay, so first thing to introduce a lemma. There is the identity of from Andrews and Bent book, and it re-expressed by Mortensen here. It's like this. and the G is defined like this one. And we can see it's very, very close to the generating function of ranks. Okay, so we just use another identity from Newton here. Use this to write this as a Lambert series. Then we just rearrange this identity. We can get this lemma. We write the generating function of ranks into 4 parts. The first part is constant, and the second and the third parts are Lambert series with some coefficients, and the last part is infinity production. So we just represent the generating function of ranks into, in fact, only 3 parts: the constant part, the Lambert series part, and the production parts. Then we just introduce some new symbol to try to write the consequence results neat. The H sub of A just represents all the production part. Okay, so just try to remember the H here. Just represents infinity production. So, for example, we can use the lemma itself to generate some identity like this. The F2 and F0 are generating function of ranks model different integers, and the H here are just the infinity production. So using lemma star, we can get the following identity. We just take the 2 here and Q here, we can get this equals to this one. And we just take the 0 here, got another identity looks like this. And you can see, in fact, the Lambert series here are almost the same. So what we have to do is just try to console this Lambert series, and then we will find the constant part are also consoled. So the only thing left are the production here. So we can get this symmetric identity here. The left side of this identity are the summation of 2 generating functions of ranks. And on the right side of this identity are 2 productions. Okay. And let's see one of the entry. If we use the lemma here, if we try to take the lemma into this kind of thing, what we will get? For example, for the left side of this identity, we just try to use the lemma to take place FA, F minus, and FB. We will find this, another symmetric identity. The left side of this identity are just equal, or we can say just represent as a summation of infinity production. And the thing is, the coefficients here are exactly same. And if we try to compare these 2 identities, we'll get this summation. The right side of this, in fact, the three infinity product can be written as this. So this means this infinity product equals to 3 summations of infinity parts. So this is one result in my paper. And let's see the sketch of proof. Because the generating function for the generating function of ranks, we have to take the roots of generating functions into it. So we can only try to deal with all the primitive roots here. And using the lemma star, we just take the root here and we will get some identity like this. And then for the series part, we can write this for this two series part. We can write the first one like this, and write the second series like this. And we can see that the only difference here is the power of alpha here is -2, and the power of alpha here is 2. So we try to cancel all the things here. We can see the only difference here, in fact, is the power here and the coefficient. So we're just taking these two kind of series into this identity, and we will see that all the series are cancelled. And the only thing left here are the infinity production. And since the roots of unity are dense in the unite circle, so we have completed the proof. Okay, so that's how to get this kind of identity from Ramanujan's entry. But the thing is, we just listed 4 entries. And in fact, we can do the same thing for only 3 of them. And 1 entry cannot work using this way. Okay, so this is my share. Thanks so much.
Okay, thank you so much for the explanation. So I think we can start for the discussion session. Is there any question from the participant first? Okay, so basically what is he doing is we have a partition, right? Partition is when we have a partition of a positive integer n, then we want to write this in terms of sum of positive integer without counting the order. And after that, we also can see, maybe we can check also via Maple or maybe another software that we know the number of partition of a number in the form 5n plus 4 is divisible by 5, and also 7n plus 5 is divisible by 7. And also we already another one with 11. So yeah, if the number of partition is divisible by 5 or 7, that's the natural question is how to make maybe 7 or 5 classes with same size, right? That's why we introduce crank, and in his problem, he tried to deal some problems with the generating function of crank. So yeah, hopefully that's the summary for the whole thing. Maybe any question, especially for this one, or maybe about the dissection. Okay, so yeah, because this kind of topic is new for us, that's why maybe need some time to wait. But maybe I have some question. So you try to make some 3 and 2 dissection, right?
Yeah.
Yeah. What happens if we see what the 5 dissection? Is it possible to do with this kind of strategy?
Yeah. In fact, if you want to get the 5 dissection, there are some results already. You can see in Renrong's paper, we just try to use almost the same thing, like here, but not using this entity. We will find another one, maybe write the generating function just using the Lambert series and try to, for example, try to divide the n, the n into the 5 parts, right?
Okay.
For example, we try to write the first part as 5n plus 1, all the power here, and then try to write another part, all the power looks like the 5n plus 2.
Okay.
And we can try to get some results using this way.
Okay. So the one that we have to dissect is this part, right? This Lambert series, right?
Yeah.
Okay. But yeah, if you want to dissect into 5 parts, it's already complicated. Even only 3 is already complicated. So
there is
so many terms, right?
There is a question. How I get the idea of this result? Okay. Thanks for the question. So for the first part, for for here. The idea to get this kind of thing, in fact, how to get the dissection is not a new thing. So we just try to find some useful identity, for example, here, or try to use another identity. We just try whether it works. And we find if we use this identity, we represent the generating function here into this, and we can just figure the 3 dissections of this M and this M here. And finally, we will get the same Lambda series as a result in another paper. So we can compare them to get the identity here. So that's the idea. Because getting the dissection is not very new thing. There are already many results. And for the second part, for this result, in fact, I just try to use the Ramanujan's result here, try to take it into this and try to see what I can get and find interest identity here. So I just take this, try to take this into the 4 entries and looks at what I will get. So it's a little bit lucky for this part. In fact, I don't know what I will get. In fact.
Yeah. Okay. Thank you. Is there any further question? Maybe. If you want to open mic, that's also fine. I think we still have some time. Okay, because this kind of stuff is very interesting in partition theory. I saw there are many papers who try to deal with this kind of stuff. And this one also related with mock theta function, right? That you have mentioned.
In fact, it's mock theta identity.
Yeah.
But you know, in fact, it's not easy to explain what is mock theta.
Correct.
Yeah. So just try to avoid using this.
Right. But mock theta is one of the hottest topic lah.
Yeah.
Trying to deal with, especially some big names in partition theory.
Yeah.
Okay. There is a further question. Maybe. Do you want me to? Okay.
By this result. Yeah, the thing is, for the dissection, if you want to get some identity, for example, like this, for example, if you want to get an identity relating the generating function of ranks modulo 5 and 25, you can try to get a dissection, maybe 5 dissection of ranks modulo 5 and modulo 25. And the thing is, you have to using the same series, and then you can try to console all the series and get an identity here. And for this thing, in fact, you can try to apply the lemma into another Ramanujan's identity and see whether there is some symmetric identity after consoling the series part. Looks like this. So this lemma can generate some identity from Ramanujan's old ones. If you want to get some further or deeper thing, I don't think this can work because this is just a lemma, right? It just represents the generating function of ranks into lambda series and the productions. So there's not too much special things here. Maybe you can try to explain it by modular form or something else. Because we know that the generating function of rank is very close to the model form, right?
Yep. Yeah, but yeah, I think for undergraduate it should be not this kind of stuff. Because the one here who is asking, Neva just passed his undergraduate program. So yeah, she will maybe start some research and also maybe try to continue for master also. Maybe she's asking to try to see whether is there any problem that she can do. But this one interesting, especially for the identity, the symmetric identity, right? For your first application, this one, yeah. Is that? Do you have any intuition before do you get that kind of identity for the symmetric one?
No. I just try to apply this lemma and find that you can get some identity and they are symmetric.
That's why, because this one look very nice, right?
Yeah, it's by coincidence.
Okay, so just trying and try to find a good one.
Yeah.
Okay. Any more questions, maybe? I think no more question. So let's give a big applause to Mr. Nankun. So thank you very much for sharing with us.
My pleasure. Thank you.
And for all participants, don't forget to fill the attendance form that I shared in the chat box. So ugm.id/algebra call April 2022. So you just click on that link and then you will go to the Google form. And please double check your name before you submit because this will appear in your e-certificate. And I think before we end our colloquium, I would like to give you an e-certificate also for the presenter. Can I share for you? Yeah. So is it okay to share my screen?
Yeah.
Okay. So
I just stop the share, right?
I think you don't have to stop. I can stop. Yeah. So this one is an e-certificate for you. And thank you very much for sharing with us, especially about partition theory, because this one is also new for us. And then, yeah, hopefully it can enhance our knowledge, especially in number theory, and especially again for partition theory. And this one is signed by our head of Department of Mathematics and also the chair of Algebra Laboratory.
Thanks.
And before we end our colloquium, can we make group photos? So hopefully all participants here can turn on the video to join for group photos. So let me wait, maybe. Okay. Actually, I also can screenshot from the recording also. So this colloquium is being recorded. So next time I will publish also, and I share to all participants who fill the attendance form. So that's the attendance form is important. Okay, so please give a big smile. 1, 2, 3. Okay, I think that's enough. So this kind of picture is very common, right, during pandemic. So again, thank you very much to Nankun for sharing with us, and I think we can end our colloquium by now. Thank you, and see you again next month, because this one is monthly from our laboratory, from Algebra Laboratory. So yeah, I don't know who's the speaker for the next one, but yeah, that if you want to keep updated, so please follow Instagram from the Department of Mathematics at mathematica.ugm. So thank you very much. See you again. Wassalamualaikum warahmatullahi wabarakatuh. warahmatullahi wabarakatuh. Thank you, Nankun. Wow.
Thank you.
That's really nice result.
Thanks.
Is it possible to get another one?
I think
That's
so.
symmetric.
If you find another identity from Room Eugene, you can just try to apply this.
Okay. But still trial and error, right?
Yeah.
Yeah.
You can just find some Moxie identity.